Hi, I'm Ben-Yaakov. This presentation is entitled Rogowski Coil Current Sensor Made Simple. Here is a typical way the Rogowski coil is used. This is the Rogowski coil. We have a loop here which is wrapped around a wire which is carrying the current. Here it is. And then there is a electrical connection here to the signal processing. Now the coil itself is made out of turns, many turns around a non-ferromagnetic core. Here it is. And then this is the wire that we want to send the current in. And the output of this winding around this non-magnetic core is fed into an integrator. It turns out we need an integrator to get a output which is proportional to the current that is now being measured. Now, the operation of the Rogowski coil hinges on Ampere's law. Ampere's law tells us that a circular integral of HDL is equal to N times I. So if we have a wire with a current, N is equal to 1 in this case, then we have magnetic field around it. And if the radius is sort of constant, a circular path here, then the magnetic field will be constant around this path. So the product of this magnetic field times the length of the path will be equal to the current. Now, if the path is not circular, it's something like that, still, if you just multiply the magnetic field at each given increment times the length of the increment, and then you add it up, this is the meaning of the circular integral, then you end up with this equation that the total product will be equal to the current. So this is the basic of Rogowski coil operation. Now the Rogowski coil has a wire, and then there is a field around this wire when the current is passing through it. Here I'm showing the field like this, and this is now is a cross section. So now if we have here a loop here, which is capturing some area, then, and assuming that the radius is constant at this point, then the magnetic field will be the current over the length of around here. And then the magnetic flux density will be times the vacuum permeability, and the flux that is captured here will be times this area. So we can say that the flux then is equal to I over L times the permeability times the area. Now, if we have a number of turns here, so the coil is made of, the winding is made of N turns, then we have to multiply by N. This is the N now of the capturing loops here, not this primary current. This is 1 here. And this will be then the expression for the flux capture, the total flux. Now, if the path is not circular, then still, according to Ampere's law, we're going to get the same number, because if you take the incremental value of the magnetic field times the distance, again, you integrate it, sum it up, you get the same value. So this is the beauty of the Rogowski coil. You don't have to have the wire going into the middle of this loop. It can be anywhere, theoretically at least. There are some parasitic effects, of course, so it's not exactly that you get exactly the same value, but it's pretty close that you can actually wrap it, the coil around anywhere, and you get the correct value. Now the coil, of course, has two ends, and it will be inconvenient if we left one end here and one end here. This would mean that in order to wrap it around a wire which is carrying the current, you'll have to have an electrical connection. So this is why usually this end now, or this wire, is now passed through the inside of this non-magnetic core here, back here. So we get the two wires on one side. So therefore we can open it here like this. Now here there is no electrical connection. This is just a mechanical connection, just to close the loop here. And the electrical connection is coming off this cable, okay? And then we have again this integral, which is very important because as we will see, the response is such that you have to correct it by an integrator. Now, looking at the Rogowski coil as a mutual inductor, we have the primary, which is this one wire going through it. It's n equal to 1. And then we have the secondary. We have here the dependent voltage source, which is equal to n dphi dt. And then we have the inductance of the secondary and the parasitic resistance. Now, if the measured current is sinusoidal, then the voltage expected here, the dependent voltage source, is dphi dt. This already includes the number of loops in the coil. And then we find that the output voltage will be proportional to the frequency, because when you take the derivative, you have here omega. So the response goes up with frequency. And you can express it in a phasor notation as j omega m is. Now, m is this value that we have found earlier, n times a, the cross-section area, the permeability, and the total length of the loop. And the units here are Henry. This is actually mutual inductance. Now, this value here is actually permeance, or 1 over reluctance, which is kind of related to magnetic units that we are used to. Now, since the response is proportional to frequency, in order to get a flat response, we have to pass it through something that goes proportional down with frequency, which is an integrator. This is why we need here an integrator. And I'm showing here something which is very popular, an integrator around an operational amplifier. Now, this network here will cause actually two breakpoints, one at 1 over 2 pi r1 c1, this is this time constant here, and one over 2 pi r3 c1, r3 and c1, this is the end of it. So within this range, it behaves like an integrator. So within this range, you're going to get a flat response if indeed the response of the Rogowski coil is proportional to frequency. So this is the way that the signal processing is usually realized, although there are some other sophisticated ways to do it. I'm not going into it in more detail. So let's have a look now at a commercial probe. This is just the Rogowski coil. This is without the signal processing. Okay, so this is this unit here by Lem. The length of this probe is 125 millimeters, and it is rated for, you see, 20 kiloamp. So this is for high current, and the response, well, here they give it as 10 kiloamp per volt or 100 millivolt per kiloamp. But this is for 50 hertz. It's fairly low frequency. So it is intended for line frequency for distribution systems. So very low frequency and very high current. Okay. Now the mutual inductance here is 321. And the bandwidth of the probe itself, okay, is about 150 kilohertz, which is pretty good, okay? And just have another look here. The coil inductance, that is the coil itself, is 1000 microhenry, which is like 1 millihenry. And this is because they have obviously very many turns in the coils in order to get a good response at the 50 or 60 hertz. Now, the parasitic resistance of the coil in this case is 113 because they have very many turns with very thin wire, which ends up with a very high resistance. Now, aside from using the Rogowski coil with just measuring current, it could be very beneficial for short circuit detection. And this is because the response is really related to the derivative of the current. And in a short, you're going to have a fast derivative. So therefore, this could be very useful as a short circuit within a short circuit protection circuitry. Now, we have found that the flux is this value, total flux, and that the total voltage now can be expressed as a function of the IDT, that is the derivative of the current. So let's take an example. Suppose we have a probe with a 100 nanohenry mutual inductance, and suppose the short has a rise time of 100 amp per microsecond. And I'm assuming that the bandwidth of the probe itself is 100 kilohertz because it is a limiting factor also. So the rise time is approximately 3.5 microseconds. Consequently, the output voltage will be the mutual inductance times 100 divided by the rise time, and I'm getting something like 3 volt, which is very nice. So we see that since the Rogowski coil is sensitive to the rate of rise of current, it is compatible with the requirements of a short circuit protection circuit. So what are the conclusions here of this presentation? We find that the advantage of the Rogowski coil is a very high current sensing capability. It can measure very high current, like hundreds of kiloamps. It has a fairly wide bandwidth, excellent response to a fast changing current. This is good for protection. And it is flexible and can be used in tight spaces. You can make the coil thin and you can actually wrap it around the leg of a MOSFET. And it has a low loss inherently. This is not like a sense resistor, which for very high current, of course, will be very lossy with a high power loss. Now, the disadvantage is that it cannot measure DC or low frequency, and it's quite a tricky signal processing. It's a bit costly, and it is not that accurate. Okay, so it's not for precision measurement of current, but it is in the range of say 1 to 2% accuracy you can get with these probes. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest and perhaps it will be useful to you in the future. Thank you very much.